Morning everyone. So in continuation to my earlier lectures on this countable and uncountable set, in this I will discuss how to show that set of real number is uncountable. So one of the method earlier I have discussed, you can refer to my lecture videos which I have given. Now to show that the set of real number is uncountable, let me recall what we mean by at most countable. So according to book of Rudin, there is a term at most countable. At most countable. So at most countable means, see, phi is assumed to be, empty set is assumed to be countable, and this one or any finite set. How to check that a set is finite? A set is said to be finite if it is similar to set of Jn. I mean, if there exists at least one bijective map between Jn and this any set, then that set is said to be finite. So where Gn is this one, 1, 2, 3 up to n. Okay, so if any set is similar to this set, then that set is said to be finite, which I have already explained. You can refer my earlier lectures. Now, and the third term is countably infinite. Countably infinite. So for countably infinite, a set is said to be countably infinite. Say a set A is said to be countably infinite if it is similar to set of natural number. Similar to set of natural number means there exists at least one bijective map from set of natural number to set of to this set, then to any set, then that set is said to be countably infinite. But some other books, as you know, that some other authors are assuming that they are saying that countably infinite, or in general they are using countable word. So that countable may be empty set, that may be a finite set, or may be countably infinite. But whatever book you will refer, whatever book you are considering, the authors will mention in starting that what notation they are going to choose. So for that, okay, let me rub this. Now I need to show that set of real number is uncountable. So for this, suppose we are going to use that this method of contradiction. So let us assume that set of real number is countable. Let set of real number be countable. So once the set is countable, we can list it with the set of natural number. We can label it. Either you use the notation 1, 2, 3, or say x1, x2, x3, or say a1, a2, a3, or alpha 1, or whatever notation you are choosing. So suppose the elements of R are denoted by set of real number by x1, x2, x3, and so on. Okay, and so on. Why we are writing this? Because we have assumed that a set is countable. So once the set is countable, we can label every member of that set with the set of natural number. This indexing only we can do, this labeling only we can do when the set of when set is countable. Now let us enclose each of the xn into an open interval. You can take disjoint open interval, no problem. This one. So let me enclose each xn in this open interval, say of distance this one. I mean the first one will be enclosed in the length 1/4 left and 1/4 right half distance. Second one as 1/2 square distance, and so on. For example, if I put let me call this as in, nth interval as this one, with nth enclosing the nth element as by in. This one is open interval. So you can see that if I put n equal to 1, for n equal to 1, 2, 3, and so on. So if we put n equal to 1, then x1 belongs to, then x1 is enclosed by this member, x1 minus 1/2 square to x1 plus 1/2 square. So you can see that 1/2 length is left to it and 1/2 square length is right to it. So the length of this interval is this minus this. So that is going to be 1/4. So 1/2, 1/4 left and 1/4 right. So it is going to be 1/2. So similarly in this way, one can this x2 minus 1/2 cube and x2 plus 1/2 cube. Similarly in this way, if we sum up length of all such intervals, then the length of the first one will be half, length of this one will be half, 1 by 4 right and 1 by 4 left, so total distance will be 1 by 2. Second will be 1 by 2 square. Third interval enclosing x3, length of that one be 1 by 2, 3, 1 by 2 raised to the power 3 plus and so on. So one can see that here it is going to form a geometric series whose first term is half and common ratio is again half. So you can use this formula a upon 1 minus r. So what we have here, 1 minus half 1. So you can see that this series sum up to 1. I mean length of each, sum of length of all intervals is 1. But xn belongs to r, but each xn belongs to r. And since we have, so union of all such xn's is going to be r. Now I can write here that r is equal to union of all such xn, where n is running from 1 to infinity. Why? Because we have assumed that this one is countable. This we are writing because we have assumed that the set is countable. I mean countably infinite because r is already infinite. And each of the xn is contained into this open interval, is enclosed in this one. So I can say from here that it is going to be contained into union of in, where n is running from 1 to infinity. Now look, if you look at the length of this one, this r, length of r is infinite, and length of sum of all such intervals sum up to 1. So a length of infinite, a set having this length infinite cannot be contained into sum of sets whose length adds up to 1. So here we have a contradiction. This means that our assumption that the set is countable, that the set of R is countable is not true. So contrary to it, the set of real numbers is uncountable. Now there are other methods. Let me recall the previous one. Yes, this one. So this proof is very simple. I have given you so the key point is that here we have used the contradiction. And another method, see, if you let me recall, already in details I have discussed in my earlier lectures, but here I just like to recall that method. See, open interval 0, 1 is subset of R, and we know that any set which is countable can never contain uncountable set. Why? See, if a set A is subset of B, and suppose B is countable, then one can always define a map from set A to set B by this one, f of x is equal to x. And clearly this map is injective. This means that, see, this one is a function. So whatever elements in domain, every element has to be mapped. And since it is injective, so cardinality of B will be either equal to A or will be greater than equal to A. So I can say that already that I have discussed. I am not giving detail here. You can look at my earlier lectures. So cardinality of A will be less than equal, and if this is countable, this has to be countable. So a countable set cannot contain an uncountable set. Now if R is countable, and already I have proved that sequence of all elements of 2 or more than 2 elements is already uncountable. Collection of sequence of all 2 or more than 2 elements. I mean, if you are using binary representation, then you can denote each member belonging to this. Suppose open interval 0, 1 is countable. Let me recall. The key idea is that we will assume that every element, all real numbers in this open interval 0, 1 are countable. And then we will try to list out all those members with the set of natural numbers. I mean sequence of set of natural numbers, and then we will try to show that there exist at least elements which are left out. I mean which are not exhausted with the set of natural number, or which cannot be labeled with the set of natural numbers. So that in details I have discussed in my lectures, that every real number in this one, if you are using binary representation, can be represented into sequence of 0, 1. Or if you are using the decimal representation, then again every real number one can write it into this decimal representation. So and suppose at each diagonal element, you can look at details of those that one. I mean how to construct such sequence. I have discussed in it my lectures on binary and ternary or decimal expression, how to write those real numbers in different expressions. So whenever you are writing in two or more than two symbols, I mean binary, decimal or ternary expression, you can always construct, even if you want to try to label it with the set of natural number, then always there exists at least one place at which at least one of the entry will differ. So in this way, one can never label every element lying in open interval 0 1 with the set of natural number. So this is the key idea. You can revise that lecture, and thus this set is uncountable. This set is uncountable, and this is the reason why R is not countable, because a countable set can never contain an uncountable set. And if some real number has two different expression, so that already I have explained in my, if you are suppose considering the binary or decimal or ternary expression, then that both will converge to a unique real number. I mean after some step every term will be finite. So that detail already I have discussed. So what I will do that after every 2-3 lectures of recording, I will discuss your doubts on via this Zoom app. Okay, so you can revise the basics from here. I will try to upload 15 minutes, 20 minutes lecture or 10 minutes lecture considering some of the standard result of theorem, and then after every 2-3 lecture I will try to discuss your doubts via Zoom. So whatever book is mentioned in your book, revise from it, and I hope that this one is clear to you. If you have any doubt, you can ask it in that Zoom discussion lecture. Okay, thank you.